Okay, I'm Jim Frankenfield, and this is another one of my problem solution videos. This problem was to come up with the equation for a sinusoidal function, um, given a couple parameters for it. And there's an equation for this. We'll see it at the end. The common approach is just to stick the right numbers into the right place in the equation. But I want to take a different approach to this and relate it to what you should already know about translating and stretching graphs. If you're studying sines and cosines, you should already know how to translate things in the plane and how to stretch things in the plane, make them taller or wider or whatever. And we can use that same thing to just get the equation we want, and we'll end up at the form that we could just plug numbers into, but I'd like to connect it to this idea of translating and stretching something in the plane. So let's review real quickly how we do that. And here in Desmos is a simple parabola, which should be familiar to you. If you're doing sine waves, you should see this already. And I can move this around in the plane by saying minus beta. Okay, so now if I take beta, and I'll explain why I'm using Greek letters later, but if I subtract something from y, if I subtract a positive number from y, that moves it up. And I can do the same thing with x. So if I change phi and if I subtract a positive number, I'm moving it to the right in the positive direction. So that's how we translate something, and I can also stretch it by putting a multiplying factor in here. So this is going to make it taller, and it'll look narrower on here, and if I go down to 0, of course, then everything is 0. And I've cut it off there, but of course if you go to a negative a, it'll be opening downward. So that's a quick review of how we translate functions. Now let's look at a sine wave. And the first thing we're told is that the horizontal axis is 5. So I'm going to change this to y minus 5, and I'm going to move it up by 5. Actually, let's, okay. So I can move this up and down just like I did with the parabola, and I'm going to set it to 5. Okay, so I've met the first criteria here. And I'm using beta because in engineering we might call this a bias. This could be an alternating current or voltage, and if we add a fixed direct DC current, we would call that a bias, and that's why I chose to use beta. So that's a bit of that comes from my engineering background. And so the next thing is that the minimums are at 3 and minus 1 and 13 and minus 1. So the bottom of this needs to be at minus 1, and right now it's at 4. So we better subtract something from, well, we can't subtract because that'll change our axis. So let's change this. And this is our stretching parameter, and if I go to 6, okay, now my minimums are at minus 1. Okay, so the x-coordinate's not right yet, but now we have the amplitude. And I'm using A for amplitude. When you look up a wave equation, you'll see sometimes K, sometimes H's, sometimes A, B, C, D. Different books and sources will use different letters. A is commonly used because it's an amplitude or size of the wave. So we have that filled in now, but we have to find this distance here. Right now this is minus pi over 2 to 3 pi over 2, so that's a distance of 2 pi Yeah. And this function k, the wave number, is equal to 2 pi over the wavelength. And the wavelength is the distance I want from here to here. And my distance goes from 3 to 13, so I have a wavelength of 10. So I'm going to put in, and this is unique to waves, this didn't correspond directly to anything with the parabola. It does correspond to stretching it, but you have to learn about the wave number. So k is going to be 2 pi over 10, or pi over 5. So let's write this as pi over 5. And let's see, now we go from minus 2.5 to 7.5. So our wavelength, or our distance between subsequent minimums, is now 10. And that's what we wanted. So we have one more thing we have to do, and that's to move this. So let's x minus, so if I subtract phi, I'm moving it to the right by phi. Yeah, I want to move it to the right, and I want to go from a, oh, this isn't 0 right now. Okay. If it's not moved at all, I was at minus 2.5. And I want it to be at 3, so I better move it 5.5 to the right. So as I increase this, I'm moving it to the right. This is just a translation, like we've done with other functions. And there we go, 5.5. Let's see, we have 3 and 13. So we have the function where we want it. So our final equation is going to be y equals a, which is 6 times the sine of pi over 5, which was 2 pi over 10, or 2 pi over lambda, times x minus 5.5. Okay, so and phi is commonly used in engineering for what we call a phase shift. So when we move this left and right, this is called a phase shift. So that's where that letter came from, and that's a common notation. And k is often used in physics for a wave number. So these are common notations, but they're not universal, and you'll see other numbers. So that gives us our answer, but it's not the only answer. Let's put this back to 0. I moved this minimum from minus 2.5 over to 3. Well, I could move this from 7.5 to 3, and now I'm moving to the left, so I have to subtract a negative. And if I subtract a negative 4.5, I'm going to be in the same place. So this could also be a minus 4.5. 4.5 and 5.5 together are 10, which makes sense. That's our total distance between them. So you can shift this left or you can shift this right. It doesn't really matter. And in fact, let's go ahead to, this distance is 10, so I can add any multiple of 10 that I want. Okay, so see, this is 1.5, it's not a multiple of 10, but if I go to 2, so now I'm adding 20. So I can shift this by one complete wavelength of 10, left or right. I can add 4 10s and I'll still have a minimum at the right place. I can go minus 7. I still have them at the right place. It doesn't matter as long as I'm shifting by a multiple of the wavelength. And this is an important concept later when you work with trig functions, and also if you get into complex variables later. So that's one thing that's different. We can have that 10n. the other thing is that a cosine looks a lot like a sine, doesn't it? And so the only difference is I have to shift this by a different amount. So instead of 0.5 now, let's see, I want this to go to 3. So I better subtract 2.5. And that's 2.5. Maybe, I guess I need to subtract 2. So here we have 3 and 13. And of course I can add a 10n to this too. I can shift it by one wavelength either direction, or 2 wavelengths, or however many I want. So there are several answers to this. Actually there's infinite many answers. Usually we don't add multiples of a wavelength like 10n. We don't usually do that. That's a factor later in some complex problems that are advanced. So usually we just stick to the phase shift. There will be between pi and minus pi, or between 0 and 2 pi. Usually it has to be within one of those ranges. But you could answer the question with any multiple of 10 there. We can also answer it with cosines instead of sines. That's just an equivalent function, an equivalent graph, and it gives you the same graph here in Desmos. So that's how you can answer that, and actually hope that helps you relate this to what you already know about shifting graphs and working with graphs in the plane and moving them around and stretching them and whatnot. So if you can make that connection, it's better conceptually than simply trying to match the right numbers to the right variables. So that's it, and I usually make the Desmos spreadsheet available. If you go to my website under video library or academic library and videos, I'll have a link to that. So for all of my videos where I use spreadsheets or Desmos, I try to make that available on my website. It takes me a couple days sometimes, but I'll get that posted, and you should be able to use the same spreadsheet. You can go back and watch the video, try your own variations, try your own numbers. You can do what I just did on your own, and that may help you reinforce it. So I hope that helps you with sine and cosine functions, and see you next time. Bye.